Okay, so yeah, as I've said, everything that's on a midterm you've seen or practiced before, particularly the paper one and the paper three. But the paper two, some of the stuff you've definitely seen before, and some of the stuff I'm not entirely sure that you've seen before. And then I was trying to suss out what things you've seen before, which ones you haven't, and then I just assumed that it'd just be good to go over all of it. So this thing right here covers all of the paper two questions for the midterm. And so these questions here will be very similar to what you might see on the midterm exam. All right. So we have a mass is attached to a spring, and it's a 3.25 kilogram mass performing SHM with a period of 2.25 seconds, and an iron block attached to the same spring oscillates with a period of 3.5 seconds. And so if it's the same spring, it would be the same spring constant. Anyway, number one, what are the conditions of simple harmonic motion? So you need to know the two conditions for simple harmonic motion. First condition, the restoring force, and thus the restoring net force, I should say. Let's throw in a caret. Net force and acceleration are directly proportional to the displacement. I threw in the net force because I was about to say acceleration is always in the same direction as the net force. Well, so then you should write net force. But so I did. But so we have restoring net force and acceleration are directly proportional to displacement. The formula for that is acceleration is negative omega squared x, where omega squared is a constant. But what about that negative? Well, that's the second condition for SHM. And the acceleration is in the direction opposite that of displacement. So that's what acceleration is negative. So acceleration is negative so long as the displacement is positive. But if the displacement were negative, then acceleration would be negative negative, which would be positive, but it's always opposite that of displacement. It's restorative. It brings the object back towards the equilibrium position. All right, number two, calculate the mass of the iron block. All right, so we're dealing with a spring mass system. We happen to know the period, and so we have two equations for simple harmonic motion, for a pendulum, and for a mass spring. T is equal to 2 pi radical L over G. Well, that's cute, but we're not dealing with simple pendulums here, so that's not our equation. We're dealing with mass springs. So T is equal to 2 pi radical M over K. Now, we're comparing two different masses that are using the same spring constant. So we solve for K. I did that very quickly over here on the right. Divide both sides by 2 pi. Then I need to get rid of the radical, so I square both sides. Then I'm trying to get K by itself, so I want K in the numerator, so I just flip both sides. I get K over M equals 4 pi squared over T squared. Multiply both sides times M, and I get K is 4 pi squared M over T squared. All right, groovy. So I'm going to need this space over here to finish this problem. And the reason why I care what K is because since it's the same K for both masses, I can set them equal to each other. So we get 4 pi squared M1 over T1 squared is equal to 4 pi squared M2 over T2 squared. I know the two different periods. I know the mass of the first block. I need to solve for the mass of the second block. Let's go. So first of all, 4 pi squared is a constant. It's on both sides of the expression. I'm not even going to bother with it. I'm simply going to cancel it. And in the end, when I solve for M2, I get 7.86 kilograms. And that's our SHM question. And then the next question involves some topic 10 and some topic 9. So let's take a look. We have two equal positive fixed point charges. Q1 equals 20, not 2.0, 20 nanocoulombs, and point P, and some point P, and they're at the vertices of an equilateral triangle of side 0.1 meters. So we have like a triangle right here, and each one of those sides is 0.1 meters. Okay, fine. Solve for the magnitude of the resultant electric field at point P. And so we have electric field from a point charge is not obviously given on a data booklet, but we can derive it. We know that E is potential difference over difference in radius, the gradient pretty much of a potential field. And we know that potential is KQ over R, so if we do potential over radius, we get that electric field strength at a point caused by a charge is negative kq over r squared, where q is the charge quantity on that object. The other way we can look at that, electric field strength is also electrostatic force per unit charge, and force is kq1 q2 over r squared. So if we do force per unit charge, we get kq over r squared. And I think that's also negative, but I'm not actually really concerned about the negative, because this just wants the magnitude of the resultant electric field. So I'm just kind of taking the magnitudes of the two positive charges. I mean, and they're both positive, so I don't have to worry about one being like a gravitational, being a electrostatic potential hill, and the other one being a well. They're both hills, so they're both going to have the same net effect. And I do have to consider the relative angles, and there will be horizontal components of this, because electric field, of course, is a vector. Electric field strength is a vector. And so there will be horizontal components of these electric fields, and it will be vertical components. The horizontal components, they'll cancel each other out, because the charge on the left will be, the field will be pointing towards the right, and the charge on the right, the field will be pointing towards the left. But the vertical components will be going in the same direction. And so they will be added to each other, but we need to find out what those vertical components are. And so we need to grab ourselves some angles. Now, it says it's an equilateral triangle, and so that means that the angles for each corner are 60, 60, and 60. And so we're looking at point P, and so point P, if we split the triangle down the middle, the angle that we're concerning ourselves with is 30 degrees, that is. And so just I kind of temporarily named the two charges Q1 and Q2. And so as an example of what I'm talking about, I put two electric field vectors on point P. There's going to be a vertical component, and it's going to be a horizontal component. And so I'm concerning myself. Like I said, since the angles are the same and the charge quantities are the same, the x components will cancel each other, because the component from Q1 will point to the right, but from the component from Q2 will point to the left. So I'm not even concerning myself with the horizontal component, but I am looking at the vertical component. And so I'm just trying to point out the geometry here. So let me zoom into it even more. So this is the point of what I'm trying to illustrate, that the vertical component of that electric field vector is going to be the magnitude of the electric field times cosine of the angle, which that's 30 degrees. And we can see from alternate interior why the angle is 30 degrees. All right, now that I've established that, and so both E1 and E2 are going to be kq over r squared cosine theta. So let's figure out kq over r squared cosine theta. And so when we work the numbers, we get 15,571.1 newtons per coulomb for each charge. And when I multiply the two of them together, I get that the combined electric field at point P is 31,000 newtons per coulomb. And then once we figured that out, number 4 is pretty much a gimme, because we've established that the horizontal components cancel each other, and so we have two vertical components reinforcing each other, and so the net electric field at P is up. This also makes sense based on the shape of the electric field for two like charges. And so based on the position of P, there's P, the net effect of the electric field at P means that at point P, the field is going up. Okay, so there's our first page. Now let's continue. There's more to this. And this is where the simple harmonic motion comes in. Okay, so now we have a new situation where point P, is moved closer to the charges. Hold on, I got kids screaming in the background. All right, so point P is moved closer to the charges, and on point P we have a negative charge. Let's remember that the two Q's are both positive charges. So 5 wants to know why that charge, little charge Q, will perform simple harmonic oscillations when it's released. Well, let's go back to what the conditions for simple harmonic motion. So first, the net force is to be proportional to the displacement. So therefore, the acceleration will be proportional to the displacement, and that is true. He says we have here that the force on the Q is roughly 200x. So yes, that's true, because F is approximately equal to 200x, so F is directly proportional to x. All right, second condition. The force is restorative back to equilibrium. Well, in other words, the force is negative relative to the displacement. And that's going to be true because the charge is negative. So yes, the two big charges are attracting the small negative charge, so making that force negative relative to the displacement. Number 6, calculate the period of oscillations of Q. Well, this is not a pendulum or a mass spring, so we can't use either of those, but we do have a formula that has period in it, and that's the definition of angular frequency. So that's great. Now that we know we can solve for the period with the angular frequency, which we totally know, right? No, we don't, so let's keep going. I don't even know what is happening in my kitchen. I just know I'd rather be in here working on solution videos. So anyway, we also have an equation that includes angular frequency, and it's A equals negative omega squared x. Let's not forget that A is F over m, and we know that F is roughly 200x. I'm going to say equals because close enough. I don't know why they said is approximately. Why can't they just say equals? Anyway, so I'm going to say it's equals for the intents of this equation. All right, so 200x over m equals negative omega squared x. The x's cancel. And so for omega, I put in 2 pi over the period. And so I get 200 over m equals negative 4, because 2 squared is 4, pi squared over period squared. And I'm trying to solve for period, so we're getting there. I'm going to give myself a little more room. I'm going to get rid of the negative on the a equals negative omega squared x because I think that force on the 200, F equals 200x, I think the negative is included in that. And also what's going to happen if I don't get rid of the negative is that I'm going to have to take the square root of a negative, and I know that these solutions don't involve complex numbers. So there. And so when we multiply both sides by 4 pi squared to get rid of it, and square root both sides to get rid of the square and a period, we get radical 4 pi squared m over 200. And I could probably simplify that further, but I'm not going to bother. I just don't really care. I can just throw my mass in there and then solve for the period. And the period is 0.2 seconds. Okay, terrific. And then number 7 is not connected to the previous problem set, which is what's meant by the Doppler effect. What does that have to do with the oscillating charge? Nothing. In fact, the Doppler effect question is actually relative to the next guy here with this oscillating plate situation. So let's write about the Doppler effect. So yeah, Doppler effect, difference between source frequency and observed frequency due to relative motion between the source and the observer. Cool. 8. So we have more SHM. And with these problems, I think they're kind of cool because they kind of combine things that we've done. Now that we've had like half the course, we're going to see some simple harmonic motion with some topic 10, or we're going to see some Doppler effect with SHM. So it's I think that's kind of neat. But anyway, so we're looking for the speed, the maximum speed of the oscillating plate. So formula for speed in SHM, we know that the speed relative to position is given by plus or minus omega times the square root of amplitude squared minus displacement squared. And we don't need the plus or minus because we're just looking for speed, so it's an absolute value. We don't know the, the angular frequency, but we know the regular frequency. And we know that frequency is 1 over the period, so I can rewrite omega equals 2 pi over the period as 2 pi f, and I'll use the frequency that we're given to get angular frequency. And so angular frequency is about 471.239, etc., seconds to the negative 1. And so, let's see, and it's looking for maximum speed. So maximum speed happens when the amplitude, not at the amplitude point, but when you're at the equilibrium point. So when the displacement, hold on, let me make sure I'm saying this right. Right, where the displacement is not equal to the amplitude, where the displacement relative to the equilibrium position is 0. So yeah, so displacement relative to equilibrium, that's where the maximum speed happens. That matters here because then I can get that Vmax. If x is equal to 0, then Vmax is omega times the amplitude. And then, let's see, so amplitude 9 centimeters, that's 9 to the 10 to the negative 2 meters. And we wind up with a maximum velocity of 42 meters per second, which is pretty fast. That thing must be oscillating pretty quickly. Actually, I think I changed the numbers here, and come to think of it, an amplitude of 9 centimeters, that with 75 hertz, that thing is shaking. So yeah, I guess the maximum velocity is 42 meters per second. That is quite an oscillating plate. Maybe the amplitude is a little high. I should have picked something a little smaller. Anyway, yeah, 42 meters per second. And so there's our oscillating plate. And it says sound frequency 3000 hertz emitted from a stationary source towards the oscillating plate. The speed of sound is 340 meters per second. What is the maximum frequency of the sound received back at the source after reflection at the plate? So this is a Doppler shift of 2 stages. There's the Doppler shift with a moving observer, and then there's Doppler shift of moving source, which is how reflections work with Doppler. And all right, so it said maximum frequency, so I'm thinking, I mean, not a maximum frequency shift, but a maximum frequency. So maybe it wants the frequency to go up. So like when I see maximum frequency, max frequency, I'm thinking like an increase in frequency. Maybe that's what they're looking for. So if it's an increase in frequency, then I would want the observer to be moving towards the source. So they would observe a higher frequency than the source. So for a moving observer, if I want f prime to be greater than f, then I'm going to be adding the speed of the observer, not subtracting it. So that's what I'm looking for. Okay, so then, all right, so there's the first shift gives us an f prime of 3370 and change hertz. Then using that f prime with the moving source from the reflection, we get using that 3370 as f prime and then shifting it even again the second time, we get 3845 and change hertz. So the max frequency received back at the source after reflection, when you control for significant figures, I mean, the 42 meters per second was 2 sig figs over here, and that was 2 sig figs because the amplitude of 9 centimeters was 2 sig figs. So I guess my final answer is going to be 3800 hertz when I round for sig figs, I guess. So there we go. I also did not substitute with units on the moving source calculation. I felt like there were enough units there, and also the IB really does not care as much about units as the Regents does. I just want to point out one other thing. Notice that on the f double prime on the moving source portion on the right, I did speed of sound minus the speed of the source because I'm looking to maximize the shift. So I want the numerator to be greater than the denominator in that case. That's why I wrote moving towards in both cases. So there's that maximum frequency. Okay, now let's go take a look at, that's the end of that guy. Now let's take a look at this diffraction pattern, which is totally different than the previous problem set. So let's give it a go. Graph shows variation with diffraction angle of the intensity of light after it's passed through 4 parallel slits. And then it says the number of slits is increased, but their separation and width stay the same. All of the slits are eliminated. Okay, so let's take a look at the questions. What happens to the angular position of the primary maxima? So the angular position is given by theta. And you have n lambda equals d sine theta, where theta is the position of the maxima. So that theta depends on which order you're looking at, which all of the different orders are given. Depends on the wavelength, which the wavelength has not changed. And it depends on, and d is the slit spacing. But it did say that the separation between them, that would be the slit spacing, and then the width of each slit, that would be b for the 9.1, the theta is lambda over b. They are the same. So all of those things stay the same. So if they're all the same, then the angular position of the primary maxima stays the same. What happens to the width of the primary maxima? And also, what happens to the intensity of the secondary maxima? Now read that carefully. That's the secondary maxima, not the primary maxima. So as you increase the slit count, more light's coming in. Each primary maximum becomes more intense. Their amplitude gets higher because they get brighter, but they also get tighter. So the fringe width actually decreases. And so even though they get more intense, they get brighter, that means in between the primary maxima, since they're getting more intense, the light is concentrating around the primary maxima. In between the primary maxima is getting less intense. It's getting darker. So the intensity of the secondary maxima decreases as a result. And it's the secondary maxima. If they said what happens to the intensity of the primary maxima, those would increase. I don't even know what is happening outside of my office door. It's supposed to be a baking party. Does not sound like a baking party. Anyway, so we have one final question, one pair of questions having to do with topic 10.2 for gravitational potential. Let's give it a go. Alright, so we have a planet, we have a star, we have a distance from the star to the planet, and we want to launch a spacecraft from the planet to escape from the entire system, and we know the radius of the planet. So what's the gravitational potential due to the planet and the star at the surface of the planet? So total gravitational potential would be from the star and from the planet, and we know that gravitational potential is negative gm over r. Alright, so we have the mass of the star, we have the distance from the star to the planet, we have the mass of the planet, we have the radius of the planet, so let's throw our numbers in. And I'm getting real tired of writing units over and over, and the IB doesn't even really care. So can we just acknowledge that the mass units are kilograms, and that the radius and distance units are meters? Of course, this guy, kilometers, needs to be meters. That we need to account for that. So that's actually 1.66 times 10 to the 6 meters. And of course, big G is 6.67 times 10 to the negative 11 newton meters squared per kilogram squared. So when you combine those two guys together, the potential from the star from the potential of the planet, we get negative 9.7 times 10 to the 10 joules per kilogram. And last but not least, right? Yes, last but not least, we have escape speed of the spacecraft from the planet-star system. And so escape velocity radical 2 gm over r. We know that gravitational potential is negative gm over r. Gravitational potential given in 13 is negative 9.7 times 10 to the 10 joules per kilogram. So I can slip in 9.7 times 10 to the 10 for gm over r. That's what I do. And so I just multiply that times 2 and square root it, and I get about 441,000 meters per second. And that is our escape velocity. Pretty darn fast. And that was the last question. Right there. So between those problems that you're seeing there, that should pretty well represent the paper 2 for your midterm. So you should be rather set with that. All right, hope that helps, and hit me up with any questions as usual. Thanks.